Welcome in another video. Okay, so in this video we are going to discuss the factors affecting the chemical equilibrium. So let's write it. Factors affecting chemical equilibrium. Okay, just focus with me. Okay, first factor is the concentration. The concentration. How does concentration affect the chemical equilibrium? So, for example, if we have something like nitrogen gas combining with hydrogen gas to give two NH3. This is ammonia, this is gas, and this is gas. Sorry, this is gas phase, and this is in the gas phase. So this is a reversible reaction. If I, sorry, if we are to increase the concentration of nitrogen gas, what will happen to the chemical equilibrium? This will lead to uh, the the equilibrium to shift to the forward reaction. What is the forward reaction? The forward reaction is the direction, or the forward direction is the direction of formation of products. That means the concentration of the NH3 will increase. The ammonia gas concentration will increase. So if I increase the concentration or the partial pressure of nitrogen, this will lead to the increase of the concentration or the partial pressure of ammonia gas. What if I decreased the concentration or the partial pressure of the nitrogen here? Simply, the reaction will shift to the backward direction. That means that ammonia gas, the two moles of ammonia gas, will decompose themselves to give back hydrogen and nitrogen. This will lead to to compensate some amount of the nitrogen lost. You got what I mean? So the reaction shifts to the direction of compensation one item. You got me? So, like, as I said, if I increased the concentration of the nitrogen, let's say we have the percentage 40%, 40% reactants and 60% products. What will happen if I increase the what will happen if I increase the concentration or the partial pressures of the reactants? This will lead to like a loss of equilibrium. This will lead the equilibrium to be lost. You got me? The 40-60% will be demolished, will be affected, will be lost. So what should we do? Or what will the system do to maintain this equilibrium? It the reactions will combine with them with each other to give back the products. So the percentage of the reactants will decrease, and in the meanwhile, the products percentage will increase. So it will maintain back the 40 and 60% again. You got me? I think you got me now. So, and the vice versa. What is the vice versa? If I decreased the percentage of the nitrogen, or I decrease the concentration of the nitrogen, this will lead to affecting this will affect the equilibrium and will demolish or destroy the equilibrium, leading to another ratio of equilibrium. It should be 40 to 60. That will lead to the reactants percentage to be decreased, and when the reactants decreases, the reactants percentage decreases, here comes the rule of the products. So they should decompose, hmm, decompose a bit to maintain, for example, the 40, 60%, as I told you in the beginning, right? So the products will decompose themselves to give back the nitrogen and hydrogen gases. I think you got me now. Okay, so that's it for the concentration. So let's talk about the effect of temperature. But but before talking about temperature, I want to write the Kc formula of this reaction. So what is the Kc formula? Let's see here. So I will write it in the form of concentrations, no partial pressures. So we have here the products, which is ammonia, NH3, to the power of 2 over the concentration of hydrogen to the power of 3 times the concentration of nitrogen to the power of 1, so I will not write it. So if you want to calculate Kc for this reaction, you will write it in this formula, right? So that's it for the concentration. I will move into the effect of temperature. Let's let's talk about the effect of temperature. So, second effect of temperature on on the chemical equilibrium. So, um, let's let's consider this reaction to be exothermic. So I will write it nitrogen, same reaction, nitrogen plus hydrogen to give ammonia. So let's consider this reaction, the formation of ammonia, is a exothermic reaction. That means I will put the heat energy next to the products, right? So let's imagine increasing up the temperature. What will happen to the equilibrium? If I increase the temperature a bit, this will lead to the shifting of the equilibrium towards the backward reaction. This is, I told you, this is the forward reaction R1, this is the forward, and this is the backward, right? So if I increase the temperature here, this will lead to the reaction to shift to the backward direction, right? But in this case, the reaction is exothermic. Just bear that in mind. This is very, very important, right? So this is in the case of, all right, in case of exothermic reaction. Okay, what if I decreased the temperature? What will happen to the concentration of ammonia gas? Okay, if I decrease the temperature, then the reaction will shift to the forward direction, and that means that the ammonia gas concentration will increase in this case. Let's consider let's consider let's consider that the reaction is endothermic. What will happen? I'll write it here. If this reaction is endothermic, I'm just considering it's not true. It's actually exothermic reaction. In case of an endothermic reaction. An endothermic reaction. Okay, let's skip this example. Let me think of another example, something like this: magnesium carbonate. But this is not a reversible reaction. Hmm. Let's say something like carbon monoxide plus hydrogen. This is the same gas, and this is 3 moles to give me H2O plus CH4. Okay. What if this is an endothermic reaction? Where would you put the heat energy? Next to the products or next to the reactants here? Of course, in case of endothermic reaction, you will put the heat energy next to the reactants, right? So if you increase the heat energy in case of an endothermic reaction, what would happen? What would happen? What will happen actually if you increase the temperature, that the reaction will shift into the forward direction, in the direction of increasing the concentration of of methane gas and water, right? So so in this case, if you increase the heat energy, the water and methane gases, both gases will both gases concentration will increase. What if what if you decrease the heat energy? So the reaction will shift to the backward direction. That means the H2O and CH4 gases concentration will decrease, and what will happen that the carbon monoxide and hydrogen gases, the concentration will increase, right? So this is the effect of temperature and the concentration. So I need to talk about the third factor, which is the pressure, but give me a sec. So the third effect, which is pressure. So, for example, the well-known example, nitrogen plus 3 moles of hydrogen will give the will give 2 moles of ammonia gas. This is a gas, this is a gas, and this is a gas, right? So, so what is the effect of pressure if I increased the pressure on this vessel? I have a vessel and I have those three gases here. What if I increased the pressure? What does it mean, increasing pressure? That means increasing pressure, the volume of the container will decrease. So in this case, if I increase the pressure, that means the reaction will be shifted towards the component which has the least number of moles. Here you have 4 moles of reactants. Here you have 2 moles of products. You have two components to consider. The first component is the reactants moles, and the second component is the products moles. You have 2 moles in the products, and you have 4 moles in the reactants, right? If you increase the pressure, that means it's not favorable for the equilibrium to have more moles, right? It wanted to maintain a certain pressure. If you increase the pressure, that means the reactants will combine together to give the components which have less number of moles to decrease this effect, the effect of pressure, right? When you increase pressure, the equilibrium is unstable here, right? Is not This is not favorable for the equilibrium, right? So the equilibrium somehow want to maintain its ratios. You got me right? So when it when it wants to maintain its ratio in case of increasing the pressure here, that means the reaction will shift into the number of moles, or the component which has the lowest number of moles, which is the products. What would happen if I to decrease the pressure? If I decrease pressure, I increase the volume, right? I increases the volume. So we have here 4 moles of reactants and 2 moles of products. If I to increase or to decrease, sorry, if I to decrease the pressure, then the reaction will move or shift to the component of the highest number of moles of gases. And the highest number of moles of gases here, we can find it in the reactants, right? So that's it. That's the effect of pressure. But, but, what if, what if I have something like, hmm, I'm thinking about something like, for example, let's say, for example, I have something like nitrogen and hydrogen to give 2NH3, or no, let me write it in a neat way, right? Let's say I have A and I have B to give C. C has 2 moles, and this is a gas. Actually, we apply the pressure on gases only. Don't apply the effective pressure on liquids. So if it comes in the exam that what would happen if you increase the pressure, if you increase the pressure of a vessel containing acetic acid and methanol, both are in the aqueous phase. What would happen if you increase pressure or decrease pressure? Nothing will happen, of course, right? Because the pressure does not have any effect on the aqueous solutions, right? It only has an effect on the gases, only gases. Just remember that, okay? So you have here 1 mole, you have here 1 mole, you have here 2 moles of C. What is the effect of increasing the pressure on this reaction vessel? On this reaction vessel here. What would happen if you increase the pressure? Nothing happens. Nothing happens, guys. Why? Because you have here 2 moles of reactants and 2 moles of products. No effect of pressure here. There is no any effect. Got me? So that's it for today. I hope you enjoyed the video. I hope you uh, understood it very well. And see you in the next video. Bye.